Happy Thursday. Today we have lecture 20, finishing up rotational kinematics. And as a quick reminder, this is not material for exam number 2. This will be on the last exam, but we got to keep it moving along. So let's go ahead and get started. So quick reminder of what we learned in lecture 19. Rotational kinematics is basically very, very similar to translational kinematics. So remember, old school kinematics is describing position, acceleration, and velocity. When we go to rotational motion, now all we're going to do is we're going to describe the angular position by this coordinate theta, which just tells you basically how far you've gone around the circle. And then I take one derivative of that, I get angular velocity, which is denoted omega z. Take another derivative, I get angular acceleration, which is denoted alpha. And the important thing to remember is that these act pretty much identically to traditional kinematics, one-dimensional motion. So all the formulas you know and love, they're going to apply. We just have to do a couple of simple replacements. The only other thing you have to remember is that in addition to specifying the total amount of omega, you also have to specify a direction, and the direction you can think of as just the rotational axis. So you point your fingers along the direction of rotation, you curl them, and your right thumb is going to give you the direction of the rotation. So there you go, rotational kinematics. Towards the end of class, we also learned that there's a connection between rotation and translation, given by this formula S equals R times theta. And so what that really means is that an object, when it moves around a circle, is also moving in space. And today, we're going to pick up with that. So here is the chart that I showed at the end of the last lecture. It's basically an analogy table telling you for each translational object, there's some analogous rotational object. So position is like theta, velocity is like angular velocity. And today we're going to learn about two of the most important concepts. Mass, which in the language of rotational motion, the rotational mass is called moment of inertia, and it's denoted I. And kinetic energy, in the language of rotation, we're going to get kinetic energy. So let's pick up with kinetic energy. In order to see this best, I'm going to actually draw this on a piece of slide here. What I want you to do is I want you to think of a few objects that are rotating within the plane of this slide. All right, so imagine I have an object M1, an object M2, an object M3. They're tied together by, rods or something. And they're all rotating about some common axis. So let's imagine the axis of rotation is somewhere in the center here. Doesn't really matter where. With a common angular velocity, omega. And of course, a common theta, a common alpha. All right. So for each of these objects, what we know from last time is that it has a velocity. For example, the linear speed of object 1 is simply omega times the radius, r1, where the radius here is the distance between the axis of rotation and the mass itself. Similarly, v2 is omega z times r2, and so on for v3. Now, these three are objects in motion, meaning they have a kinetic energy. And I can just write that down using the formula I know and love. 1/2 mass m1 times v1 squared plus 1/2 m2 times v2 squared plus 1/2 m3 times v3 squared. Plugging in these formulas, I have 1/2 m1 times omega z squared r1 squared plus 1/2 m2 times omega z squared times r2 squared, and so on for however many other objects there are. And now the nice thing, I'm going to go ahead and factor out that factor of omega z squared. So what I'm left with is 1/2 m1 r1 squared plus m2 r2 squared plus m3r3 squared, and so on if there are more masses, times omega z squared. So what you see is the regular old kinetic energy can be written as 1/2 of some object times angular velocity squared, so kind of like 1/2 mv squared. And this object in brackets is called the moment of inertia, I. It's worth quickly noting that it's not like this is a new type of kinetic energy. These are just regular old kinetic energies, 1/2 mv squared. The difference is that now if I consider the object as a whole, so if I consider these 3 point particles as one big object, the whole object is really not moving together. It's rotating. And so I want to think of translational motion as having its own kinetic energy. And here is the rotational kinetic energy. So this is only coming from the rotation. So here we go again. That's that same formula I wrote on the previous slide. And I'm going to identify the object in parentheses as this moment of inertia I, or sometimes I'll call it IZ to indicate that it's the moment of inertia about the z-axis. So there you go. Rotating objects also have kinetic energy. I can write it pretty much analogous to translational motion as 1/2 I omega z squared. And the moment of inertia is the rotational equivalent of the mass. Now I want to emphasize that doesn't mean it is the mass. That's not a meaningful statement because, for example, the units are completely different. Notice that the units of moment of inertia are mass times distance squared. So that's going to be kilograms times meters squared. So it's not that it's a mass. It's this bizarre object with units of kilograms meters squared, but it plays the role of the math. If you use, plays the role of the mass mathematically. So if you go through all the math of rotational motion, it looks exactly like a mass from translation, but now in terms of rotational objects. Alrighty, so that's my moment of inertia. And the important things to remember about this formula. So if I have a bunch of point particles, it is simply defined as the sum over all the point particles of mass times radius squared. So m1 r1 squared plus m2 r2 squared plus etc. The things to remember in this formula: r is the distance from the axis. It is not the distance from the origin. This is not the coordinate. This is the distance from the axis. And because of that, the moment of inertia will actually depend on your choice of axis. So as an example, here is a rotating object. You guys are going to see my Apple Pencil here. If I rotate it about the center versus if I rotate it about the end, everybody can kind of see I'm rotating about the end versus rotating it about the center. Those will have completely different moments of inertia. We'll actually solve for those later in the lecture. But it's very, very important. Moment of inertia will depend on the choice of axis. So let's start by trying out an experiment. Let's see if we can actually change our moment of inertia. So I want everyone to pause the video for a second. I want you to grab 2 of the heaviest objects you can find. So for me, since this is a physicist's house, the heaviest objects I could find are a bunch of textbooks, though if I'm being perfectly honest, they're actually medical textbooks, but such is life. So here you go, very heavy objects. And what I want you to do with these heavy objects is as follows. So try to sit in a chair. If you don't have a rolling chair, the other option you can do is just stand up. Just stand up and hold these guys out. And what I want you to do at first is to take your heavy objects, hold them close to your chest, and try to spin around. If you've done everything right, it should be pretty easy. Okay, it shouldn't require a lot of work to spin around. If you prefer, you can stand up, try to go around in a circle. It should be pretty easy. Now what I want you to do is take those exact same books. I'm not changing mass at all. The mass is the same. Hold them out as far as you can. If, like me, you are very weak now and can't do that for very long, then, do this very, very quickly. And then I want you to try to rotate around. And what you should find is that it's very hard And then when you bring them in, you actually start to speed up. It becomes very easy. So very hard, bring them in, speed up, it gets a lot easier. Use your physics textbook, which most of you bought, right? All right, so what does that tell us? When I'm doing that, when I'm bringing those objects closer to me, what I'm doing is I'm changing their radius. I'm making their radius smaller. So what that tells us is that taking the exact same masses but bringing them to smaller radius is going to decrease my moment of inertia. And moment of inertia, again, is like mass for rotation. So if you have a very large mass, it's very hard to push you. If you have a very large moment of inertia, it's very hard to cause you to rotate. So when I held those books far out, I had a very large moment of inertia. It was hard to cause myself to rotate. When I brought those books in, small moment of inertia, it became much easier to go ahead and rotate around. All right, so that's some of what's going on with moment of inertia. Let's go ahead and start with our first example of this. So consider 3 balls of equal mass m connected by massless rods, forming this equilateral triangle. And we're going to consider 3 axes. Axis A is going to go through the top ball like so. Axis B is going to go through the bottom right ball like so. And axis C will be right here in the middle of all 3, so it's equidistant to each of those masses, and it's going out of the plane of the page. All right, so the first thing I want you to ask yourself is, what is the axis among these 3 that I've drawn with the smallest moment of inertia? Is it A, B, or C? So the first thing to say about this is the mass term doesn't matter at all. The formula you're going to use is I equals sum on the particles of mass times radius squared. But notice that the mass is just a constant, so we don't have to worry about that. What we want to do is we want to minimize r squared, the distance from the center, from the axis. All right, so again, take a look at this problem. Which one of these 3 has the smallest moment of inertia? Okay, so the answer is going to turn out to be A, as we will see. And we can actually see that pretty easily. So first off, A has no distance to this top particle. It has distance A over 2 to the rightmost particle and A over 2 to the leftmost particle. By contrast, axis B has 0 distance from one A over 2 to another, but then all A to this third object. So that's a pretty large mass. And with axis C, it has non-zero distances for all of them, and each of those distances is a little bit longer than A over 2. So when you add these all up, it's going to be a pretty large moment of inertia as well. So now what I want you to do, I want you to take a few minutes, use this formula. It's just geometry now that I'm asking you to do, and figure out what are the moments of inertia about axis A, B, and C. And if you've done everything right, you should find that A is in fact smallest. All right, so I'm going to go ahead and assume that you've paused the video, solved this problem. Let's go ahead and go over the answer together. So quickly to redraw it, what we have is 3 balls of equal, let's call them point particles, so they're very small, of equal masses m, and we're interested in 3 axes of rotation, A, B, and C, which is passing out of the plane of the board and equidistant to each of these particles. So the first axis that we're going to be interested in is axis A. And so for the purposes of illustration, I'm going to go ahead and label these 3 identical particles as 1, 2, and 3. So I can write out their distances. For axis A, R1 is equal to A over 2, as I drew on the previous slide. So it's half of the length of a side. That's A over 2. Similarly, R2 is A over 2. And since object 3 is right on that axis, it's concentric with it, R3 is actually going to be 0. There's no distance. Again, it's not so easy to draw, but you should really be thinking of these guys as point particles. You should be thinking that they're so small that the actual radius of the spheres themselves doesn't matter. All right. So we have R1, R2, R3, and then we have our handy dandy formula. I is equal to sum on m times r squared. So that's m1, which is m times r1 squared, a over 2 squared, plus m2, which is m times a over 2 squared, plus m3 times r3, which is 0 squared. So that's m times 1/4 a squared, plus m times 1/4 a squared, plus 0. And 2/4 is a half, so this is 1/2 m a squared. That's the moment of inertia about axis A. Next, let's talk about axis B. Axis B is going to push through this rightmost particle. And so now R1, the distance between this axis and object 1, is a whole side length, a distance A. R2 is 0. The axis goes right through particle 2, so the distance is 0. And finally, R3, the horizontal distance between this axis, remember this axis is the whole line, so we want the point where it gets closest, and particle 3 is again half a side length, which is a over 2. I add these up. My moment of inertia is m times a squared plus m times 0 squared plus m times a over 2 squared. And that's just ma squared times 1 plus 1/4 is 5/4. And notice, as predicted, this is larger than the moment of inertia about axis A. Next, let's talk about the moment of inertia through axis C, which is equidistant from each of the masses. So equidistant means that the distances here are all equal. R1 equals R2 equals R3. And all we have to do is a little geometry to figure out what exactly that could be. So there are various ways to do this. My personal preference is as follows. So I'm going to go ahead and try to draw it down here. Here's my equilateral triangle. Here's my point C that's equidistant to all of them. And if I draw a line that goes from here to there, it has to bisect this side of the triangle. We know that each one of these angles was 60 degrees, so that means this smaller angle is 30 degrees. And now it's pretty straightforward trig. So I have half the side length over here, a over 2. I have a 30-degree angle, and this distance right here, which is the distance I'm after, is the hypotenuse. So cosine of 30 degrees is adjacent, that's a over 2, divided by hypotenuse, let's call that, I don't know, r. And we want to solve for r, so r is a over 2 times cosine alpha, 2 times cosine of 30 degrees, sorry about that. Cosine of 30 degrees, some of you might remember, is the square root of 3 divided by 2, so the radius is a divided by the square root of 3. And now that's the same for each of the objects. So I is just m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared. All the m's and the r's are the same, so it's 3mr squared. And now just plugging in that r is a over root 3. This is 3m times a squared divided by 3, or just ma squared. So despite all that annoyance, it ends up being a really nice answer. But again, ma squared is larger than 1/2 ma squared. So within the context of what we've seen here, IA is still the smallest of the moments of inertia. Okie dokie. So that's moment of inertia. Now, we can do more calculations using point particles, but in real life, that's rarely what we have. In real life, what you usually have is some solid object. I want to calculate the moment of inertia of my iPad, or I want to calculate the moment of inertia of a coffee mug. It's some solid object, and we don't yet really know how to do that. So the way we're going to do that is kind of similar to how we treated a few other problems. Certainly, if those of you have been going to my little calculus after classes, we've done this a couple times. We take our complicated rigid body here, just this rectangle, for example, and we're going to break it up into little pieces. So each of these little pieces I'm going to think of like those point masses. It has some mass, it has some distance, r from the origin, r from the axis of rotation, it has some small mass dm. The d indicates it's small. And then my sum over all of these objects, when I take the limit of having these objects become smaller and smaller and smaller, we know what we're doing here. That's called an integral. So this formally can be expressed as an integral, r squared dm. Now, for the purposes of this class, we won't actually be calculating too many of these integrals. It's not something that, any of these integrals, I should say. It's a little beyond the scope because you, generally speaking, need multivariable calculus. But what I do want to say is that in most cases that you'd be interested in, so for example, if an object has constant density, meaning it has a constant mass per unit volume, so if it's made of a single material, for example, gold has a certain density you can look up on the periodic table, and when you plug that in along with the shape of the object, you will generally have a very nice form of this integral. And if you have an object with multiple components, let's say I have, a Tetris piece shaped object rotating around this axis right here, what I would do is I would first calculate the moment of inertia of the first half, then calculate the moment of inertia of the second half, and then just add them up. The total moment of inertia is just the moment of inertia of one half plus the other half. So break it up into smaller pieces, add them up, and you will get the total moment of inertia. Now here's the table that I've stolen straight out of the book for your moments of inertia. There are various things here. A slender rod is like a line-like particle, rectangular plates, hollow cylinders, solid cylinders, and then even solid and hollow spheres. Nothing very exciting to say about this besides these are all correct statements. And the other thing that's worth saying is I will give you this information on the exam. So this is probably a little bit moot this semester because you can, of course, look this up either in the book or on the web in 2 seconds. But I'm not going to try to make you do that. I will either give you a lookup table or I'll just give you these numbers or give you these formulas on the particular problems where they're interested. For those who do care a little bit more about class, after calculus, after class, so kind of at the end of these lectures, I will derive this formula. So you can see a little bit of where the calculus comes in on this one. But for now, we're just going to take these as given and go ahead and work with them. So now let's put this together and actually try to solve a problem that you might actually care a lot about. So consider this flywheel. A flywheel is, an object kind of shaped like this. The radius is 1 meter. It's made from 6 thin spokes of mass 12 kilograms and an outer rim of 221 kilogram mass. The question is, if it's rotating about the center, and you can forget about this little bit in the middle, you can convince yourself that's a pretty small moment of inertia, as we saw. So just considering the spokes plus the outside, what is the moment of inertia about the center? My hint to you is break it up into small pieces, solve for each individually, and then add them up in the end. All right, so take a quick minute. You may want to go back a slide to your formula sheet. Okay, so at this point, I'm going to assume you've tried to solve the problem. As I mentioned, the way you're going to want to do this is you're going to want to take the information we're given. The radius of the tire is 1 meter. The mass of the spokes is 12 kilogram. Mass of the rim is 221 kilogram. And figure out how to break this up into pieces that we know. So take a look at these 9 formulas. Which of these is relevant for the spokes and which of these is relevant for the outer rim? So the answer turns out to be the slender rod, because each of these spokes is a slender rod rotated about its end, 1/3 ml squared, and the hollow cylinder. So this doesn't really look like a cylinder, it really looks like a circle, but I could have that cylinder be relatively flat. You'll notice it doesn't actually care about the height of the cylinder. That does not enter into the formula. So I can flatten that out. I get that my moment of inertia is mr squared, where r is the radius of this rim. And then we're good to go. All right, so we're going to do the spoke and the rim separately, then we'll add them up at the end. We'll start with the spoke. We saw that the moment of inertia of each spoke, it's like a slender rod about its end, which turned out to be 1/3 the mass of the object, which in this case is the mass of the spoke, times the length of the spoke squared. And in this case, the length of the spoke is just the radius of the cylinder. So the moment of inertia of each spoke is 1/3 the mass of the spoke times r squared. And I've given you all these numbers so you can plug them in if you like. The moment of inertia of the, there we go. Moment of inertia of the rim is similarly, so this is just the thin-walled cylinder. So for that, we just saw that it was the mass, which is the mass of the rim, times radius squared. And the problem asks not for these individually, but for the total moment of inertia, which we just add them up. So the total moment of inertia is that of the rim, plus that of each spoke. So there are 6 spokes, meaning that I have to multiply 6 times the moment of inertia of the spoke. And now you can go ahead and plug in some numbers here. It's not too bad. The answer turns out to be 243. And then reminder, what are the units? Kilograms times meters squared. Not particularly informative. The units are not that interesting, but you will need to remember that. Alrighty, so that's moment of inertia. Use these formulas. Use your handy dandy table. Make your life easier. Don't try to reinvent the wheel. And now, before we talk about this last concept of the day, I want to talk a little bit about something that some of you may have already seen. So this was covered very briefly in Lecture 18. That was that optional lecture that I put online. So you don't need to know all the material from that lecture. There's only one little piece of information that's going to show up again, and that is the concept of the center of mass. So for those of you who have already seen this, I apologize. You can feel free to skip through. For those of you who haven't, here's a reminder of what you actually do need to know. So when I have multiple objects, for example, the multiple point particles we had previously, or the Earth and the Sun and the Moon, which is the example I went through in Lecture 18, you're welcome to go through that again to get some practice. So here I have 3 different objects. I have, let's say a sphere down here, I have a cylinder over here, and I have a bar right here, or a slender rod. And I want to know what's kind of the middle of these 3 objects. So you can imagine they're all tied together by massless rods. I want to know what's the middle of these 3 objects. What's the natural point that's kind of smack dab in the middle? So that is actually something that's very useful to define. We define it as this thing called the center of mass. The center of mass is the point that is kind of the average position in the object. And it's defined by this formula. The position of the center of mass is mass 1 times position 1 plus mass 2 times position 2, etc., divided by the sum of all the masses. So it's kind of a weighted sum of all the positions of the objects. Now, in most of the situations we're going to care about, for example, the rod itself, this is going to be pretty obvious. So if I have a rod of length L, where is the center of mass going to be? Halfway along the rod, right? It's kind of in the middle. It's intuitively, there's no other place that would be in the middle besides right here. If I have a sphere, what's the center of mass? Well, it's the center of the sphere, similarly with a cylinder. So for each of these objects themselves, which has high symmetry, don't overthink it. It's just the middle of the object. But then if I want to consider these three together as one system, for example, a rotating object made of some funky parts, then I do actually need to go to the formula. So the position of the center of mass is given by this formula, and there's nothing else I can say. You simply plug in that formula. It kind of tells you where is the middle of this combination of objects. So center of mass is going to turn out to play a rather important role in rotational motion. In fact, most of what we've been talking about so far, the center of mass was kind of there, whether you realized it or not. But what I'd like you to do, quickly take a couple minutes and tell me for these three balls, so going back to example number 1, these three balls in an equilateral triangle and defining the origin of the xy coordinate system. Here, let's just be very clear. X is in the usual way, y is in the usual way. So the origin is written. What is the position of the center of mass? So take a minute. All right, so I'm going to assume that you've done that. Let's go ahead and see how to do this properly mathematically. So as you might have guessed, just based on the way I introduced it, the center of mass coincides with that axis C that I had drawn. So here are my three spheres, my 3 point-like spheres. Here's the origin of my coordinate system. And if I want to know where is the center of mass, it's pretty straightforward. I simply have to figure out what is the position of each of these objects and then add them up via that formula. So for example, let's talk about object 1. What is its y component? 0, right? So y equals 0 is this axis right here. The y component of object 1 is just 0. What's the x component? That's a little bit more complicated, but it's not too bad. It's half the side length as we've seen before. So that means it's negative a over 2. Negative because it's off to the left. And similarly, R2 is going to be positive a over 2, comma 0 in the y direction. R3 is a little bit more annoying, but not too terrible. So what's the x component of R3? That's the easy one. It's 0. The y component, we have to do a little bit of trig. So here's my equilateral triangle. And now it's not too bad. I can drop a line vertically from this point. I know this is 60 degrees right here. And the problem is asking for the opposite. So this is the y component, y3, is opposite the 60-degree angle, and the hypotenuse here is a. So that's simply a times sine of 60 degrees, and sine of 60 degrees is like cosine of 30 degrees is square root of 3 over 2. So that's a root 3 divided by 2. And now I just need to take these positions, plug them into my formula. Position of the center of mass is equal to m1, which is m, times r1, negative a over 2 comma 0, plus m2, which is m, times r2, a over 2 comma 0, plus m3, also m, times 0 comma a root 3 over 2. That's that last one. And we're going to divide that by m, the total mass. So this turns out to be pretty straightforward. These first two terms cancel each other out. This last term does not, but the m's do in fact cancel. And what I end up with is 1/3 of 0, which is 0, and 1/3 of a root 3 over 2, which is a divided by 2 times the square root of 3. So there you go. You can quickly confirm for yourself that this is the same exact point as that axis C that I had drawn earlier. And now, just as a quick check, so here we have those same three axes that I drew earlier, A, B, and C. The point labeled C is indeed the center of mass. So what I want you to tell me is which of these axes pass through the center of mass. A, B, or C? So the answer is A and C. See, it's pretty obvious because that's passing directly through the center of mass out of the page. A is also pretty obvious because here is the point that I'm passing through, and you'll notice the line goes right through that point, and then B does not. Okay, so A and C pass through the center of mass, B does not. Now, why am I asking you about this? Well, it will turn out that there's this one nice formula that relates the center of mass to the moment of inertia. So here we are. It's called the parallel axis theorem. And the idea is as follows. Imagine I told you there was some axis that passed through the center of mass. Those could be A or C. Those are both completely valid choices. But some axis that goes through the center of mass, I told you the moment of inertia. And then I took a parallel axis. So not some other random axis, but an axis that is parallel to the original one, a distance d away, and I asked you what's its moment of inertia. What you can show, and what is shown in the notes, and I will actually do this after class as well, is that the moment of inertia at a distance d away from the center of mass is just the moment of inertia at the center of mass plus the mass of this funky shaped object times d squared, where d is the distance between them. Okay, so the moment of inertia through axis B, which is not through the center of mass, is equal to moment of inertia through the center of mass plus md squared. If you look at this formula, you can notice something really important, which is the minimum value of the center of moment of inertia will always be something that passes through the center of mass, because md squared is always positive, meaning anything I do that moves me away from the center of mass is going to increase my moment of inertia. So that's the important mathematical and physical concept here, is that if I want to make rotation easy, if I want to make my moment of inertia as small as possible, I want to be sitting on an axis, or I want to be rotating through an axis that goes through my center of mass. Okay. So let's go ahead and see how we can use this. Let's say I were to tell you that the moment of inertia of the object on the right, which is the slender rod going through its center, is 1/12 ml squared. Then what's the moment of inertia through the end of the rod? All right, so this you can actually look up. It's in the table. But we're going to go ahead and use our parallel axis theorem. So I'm just going to go ahead and write it back up here. I through a parallel axis is I through the center of mass plus m d squared, where d is the distance between them. So what's the distance between this axis and this axis? Well, it's L over 2. It's half the length of the rod. So d is L over 2, mass is m. And now we just need to plug that into this formula. So here I've actually told you the moment of inertia through the center of mass. I haven't told you IB. So in this case, IB, let's call this axis B, is I through the center of mass which is 1/12 ml squared plus md squared. So mass times distance, L over 2 squared. That's ml squared. That factorizes times 1/12 plus a quarter. And you can quickly check this. A 12th plus a quarter is a third, which is exactly what we had from the previous table. We can do this the other way around as well. So consider the following situation. I have this square plate, and I tell you that its moment of inertia about this axis that passes through this edge is 1/3 ma squared. What's the moment of inertia through this axis that passes through the center? So take a quick second, see if you can figure it out. Okay, good. So this is another application of the parallel axis theorem. We have two parallel axes. The distance between them now is A over 2 half the side length of that side. But now I've given you the moment of inertia about a non-center of mass axis. And I'm asking you about one that's through the center of mass. So it's just a slightly backwards use of this formula. I have IB, which is 1/3 ma squared, is equal to I about the center of mass. They're parallel axes, that's very important, plus the mass times distance, a over 2 squared. And when you solve this for I center of mass, you will find 1/12 ma squared, which is indeed correct. And is what you'll find in the formula sheet. All right, so that's the parallel axis theorem. It is really useful because once I tell you one piece of information, let's say the moment of inertia through the center of mass, any of the other axes are going to be pretty straightforward. So finally, let's go ahead and put these guys together to talk about rotational kinetic energy. Imagine that you're the head of a power plant and you want to store energy in a wheel, the shape of a uniform disk. So the wheel is going to be made of iron. The density of iron is 7,800 kilograms per cubic meter, and it has a thickness of 10 centimeters. So what I want you guys to do is figure out what radius of disk is necessary to store 10 megajoules while spinning at 90 RPM, revolutions per minute. And then we'll talk about B and C together, actually. All right, so start with A. Let's figure out what is the radius required to store this amount of energy. All right, so at this point I've assumed that you've done this problem. Let's go ahead and go over the answer together. So this one's a tad more complicated, but it's not too bad. First off, let's identify what we are given in this problem. So we're given a flywheel, which is a disk, so a uniform disk rotating through its center of mass. On my handy-dandy formula sheet, I can figure out, so the moment of inertia of this guy, it's going to be one we're going to use a lot. So the moment of inertia of a disk, you're going to want to remember this, is 1/2 mr squared, where r is the radius. We are given the shape, we are given the density, rho, which is 7,800 kilograms per cubic meter. We are given the width of the disk, or let's call it the height of the disk, which is 10 centimeters or 0.1 meters. We're given the amount of kinetic energy, and in this case it's rotational kinetic energy, which is 10 megajoules, or 10 times 10 to the 6th joules, so 10 to the 7th joules. And finally, we're given omega. We're given how fast it rotates. So we're told that it rotates at 90 rotations per minute, RPMs, 90 rotations per minute. Now, as always, we're going to want to convert this to SI units. And for rotation, that means radians per second. So as we did last time, first we're going to convert by using that 2 pi radians, or 360 degrees, is 1 full rotation. It gets rid of the rotations. And we're going to also multiply this by 1 minute divided by 60 seconds, which will give us radians per second. So when you plug in these numbers, this turns out to be 9.425 radians per second. This is all we're given, and we want the radius, r, of the disk. All right, so it's not too bad. We know that the kinetic energy of rotation is 1/2 I omega squared. We know omega, we don't know I. So let's go one level deeper. I, as I mentioned, is 1/2 mass times radius squared for a cylinder. We don't know m. We don't know r, but we're going to figure that out. so there's no need to do anything here. Let's see what we can do for m. So we do know that the density, rho, is mass divided by volume. So this is something we're going to use a lot in these sections. Mass divided by volume is density. And for a cylinder of surface area A and height h, the volume is just A times h. The area of a circle is pi r squared, so that's pi r squared times the height h. Density is mass divided by pi r squared h. And now, since we know everything in this formula except for mass, let's go ahead and solve for mass. Mass is pi r squared h times rho. Brought these guys over to the other side of the equation. I'll plug that in up here. I get that moment of inertia of the disk is 1/2 mass pi r squared h rho times r squared, or in other words, it's 1/2 h rho times r to the 4th. I dropped the pi at some point, sorry about that. Pi over 2 times h rho r to the 4th. And finally, I'm going to plug that in up into my original formula. I have that my rotational kinetic energy is 1/2 I pi over 2 h rho r to the 4th times omega z squared. And now I want to simply solve for my radius r. Okay? So I'll bring everything over to the other side of the equation. I have r to the 4th is equal to 4 times k rotation divided by everything else in this formula, h times rho times omega z squared times pi. Okay, so I brought everything over to the other side. I take this guy to the 1/4 power. I take the 4th root if you prefer. And I get that my radius is the 4th root of 4k rotation over pi h rho omega z squared. That's just algebra. And then I go ahead and plug this guy in, and it turns out it's actually not so crazy, 3.68 meters. So this is not such a crazy set of numbers. 10 megajoules is not an infinite amount of energy, but it's not a small amount of energy either. The kind of upshot of this example is that rotation is actually not a bad way to store energy. We're going to see this. Rotational motion is actually preferred in many cases for storing energy and for doing a lot of interesting things. So anyways, that is the solution to part A. What is the radius that I need in order to solve this? About 3 meters, or 3.5 meters, which is about, 12 feet, somewhere in there. So next, does K rotation increase, decrease, or stay the same if we pivot the disk about the edge instead of about the center, while keeping everything else constant, except for the energy, obviously? Okay, so the answer is K rotation increases. What I want you to imagine for this part is that instead of rotating around the center, we take this disk and we rotate around the edge. And what we knew is that the I about the edge, one second here. So I about the edge is simply going to be I about the center plus mass times the distance between them squared. That turns out to be 1/4 mr squared, but it doesn't really matter. The key point is this is larger than the moment of inertia about the center of mass, which is what we had before. So since my kinetic energy of rotation is 1/2 I omega squared, if I goes up, this guy is going to go up. Similar question. Does K rotation increase, decrease, or stay the same if we replace the disk by our wagon wheel from the previous example? So this object that had, oh my gosh, I have to go very far back here apparently. Very good. This object that has most of its mass around the rim. Does k rotation increase, decrease, or stay the same if we do that while keeping mass, radius, and omega fixed? So again, it's going to go up. The answer for this comes from noting that for a cylinder or a disk, I is 1/2 mr squared through the center of mass. For a ring, where most of the mass is concentrated on the outside, and the wagon wheel is almost that. There's a little bit in these spokes, but mostly it's around the rim. I is going to be mr squared. So it's doubly as large as the disk. So if I really want to store as much energy as possible, what I want to do is I want to use this very, very thin, these very thin spokes, and then focus my mass around the edges. So that turns out to be really important in many examples. Bikes, for example, that's the reason bike tires look like this, is they're trying to push all of that mass to the outside. They're trying to make the moment of inertia of the bike tire as high as possible while the mass stays very low. Because as we'll learn maybe very briefly towards the end of next chapter, that's going to help stabilize the bike. It's something called gyroscopic stability. And it's the same piece of physics that actually is responsible for gyroscopes, which is another example of this. All right, so that's all that we have to formally cover in this section. That's all that will be on the exam. For those of you who aren't so interested in doing a little extra calculus, a little extra algebra, that's perfectly fine, I understand. Good luck on the homeworks, good luck on the exams. I will be in touch about the exam if I haven't already. So keep an eye out for that. That's obviously the most important thing coming up for most of you. For those of you who are interested, I'm now going to take a couple of minutes and talk about just a little bit of the math behind the moment of inertia, the parallel axis theorem, and about how to use calculates to calculate moments of inertia. All right, so the true believers have stayed on. We have a little bit of extra material here for those who are interested. So there are two things I wanted to talk about, just to get a flavor of what you could be doing with this. First thing I wanted to quickly mention the parallel axis theorem. So there is a proof in the notes. It's perfectly correct. There's absolutely nothing wrong with it. But as I was on a walk earlier today, I was, thinking about this because that's what physicists do, sadly. And I realized there's another slightly different way of doing this, which is a little bit more fun because it uses vectors. Gets a little bit of practice with vectors. So let's take a quick look at how we can do this a little bit less formally. A little bit less mathematically. So imagine I had the following funky looking shape, which again I'll discretize into a bunch of little particles, M1, M2, M3, blah, 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 blah. So I know that my moment of inertia for many, many small particles is the sum over all those particles, let's call them J. J equals 1 through however many particles there are, of mass times radius squared. And let's in particular imagine that I start out with a moment of inertia that goes through the center of mass. So my axis is going to start out through the center of mass. Furthermore, since it doesn't really matter, I can go ahead and cheat a little, and I can make my center of mass simply be the coordinate 0, 0 within the xy plane. I'm allowed to do that because I could just basically redefine my coordinate system. And now, so I'd mentioned that these r's aren't really positions, they're radii. So r, kind of rj, in this formula is the magnitude of the position, the magnitude of the object, where the object sits, minus wherever my axis is. But in the very special case where my axis is sitting at 0, 0, then rj is really just the position of the object. So in this particular nice coordinate system, my center of mass has just this really nice formula where I can interpret Rj as just the position of the object. All right, so now imagine that I shift to some other axis that's parallel, so it's perpendicular to the page here. It's parallel to my center of mass axis, it's perpendicular to the page, and the distance there is d. In fact, I'm going to make it a vector, d, that goes from one to the other. So how does that change? Everywhere I had originally Rj, I now have Rj minus this new displacement, d. So if Rj had been sitting right at this new axis, now it becomes 0. Otherwise, it shifts by this amount d, which is a vector. So let's go ahead and plug that into the formula. My center of mass about this new axis, my moment of inertia about this new axis, which I'll call capital B, exactly as in the formula, is simply a sum over all my masses, j of mj, times my new radius, which is rj, minus displacement d squared. What do I mean when I talk about the magnitude of a vector squared? Well, this is really just a dot product. What this actually means is rj minus d dot product with rj minus d. And I can go ahead and do this dot product. So rj times rj, that's just rj squared. D times d, that's just d squared. And finally, I have d times rj and rj times d. So that's minus 2d dot rj. Good so far? All right, so now let's go ahead and continue with this formula. I have a sum over j of mj times rj squared. Aha, that's just my original moment of inertia. Plus sum over j of mj times d squared. But aha, d squared is just a constant. So the sum over mj is just the total mass m. All right, and so it seems like I'm going to need this last term to go away. And let's go ahead and see how that happens. So I have minus 2 times the sum over sites, j, of mj d dot rj. And this is where it gets a teeny bit tricky. So the thing that I can tell you is that the dot product has a certain associative property, which is that if I have mj times d dot rj, I can also write that as d dotted with mj times rj. That's just saying that I can multiply the constant before or after I take the dot product. It doesn't really matter. Now notice again that d is a constant, so I can actually factor that out of this sum, which is a little weird to do, but I'm going to go ahead and isolate this term right here. So I have negative 2 times d dotted into this whole sum on j of mj times rj. This may look a little opaque, but if you remember my definition of the center of mass, my center of mass was by definition m1 times r1 plus m2 times r2 plus dot over the sum of the masses. You'll notice that this object in parentheses actually just looks like the numerator here. Or in other words, the sum on j of mj times rj is just the total mass times the position of the center of mass. And that turns out to be true. And so finally we have our proof. If the position of the center of mass is 0, which is how I defined it originally, d dotted into the 0 vector is 0, and what I'm left with is ICM plus MD squared, which is the parallel axis theorem. Or if you like way more math, you can find that in the notes. They both give the same answer. One's just a little bit prettier than the other. All right, so that was vector calculus or vector algebra. Now let's do some calculus. So it's actually kind of a pretty piece of calculus, how to derive the moment of inertia. Something the first time you see it, it kind of feels a little bizarre, but it's very pretty. And the more and more you get used to it, it's something that it's very useful. Again, it's quite similar. I don't think anyone stayed for this, but when you wind a rope around a circle with static friction, it's what causes this exponentially large frictional force. It's what causes, it's the same technique that we're going to use for a ton of other things if you continue on beyond this class. So it's a very useful technique. Here I'm going to show you how you can derive moment of inertia with this basic technique, where again, this basic technique is breaking the thing up into small pieces and then adding up those small pieces. All right, so rather than giving you the general idea, it's hard to do a general idea, to be honest, and I'm not a mathematician, we're going to simply go over a few examples. We'll do 3 kind of increasingly complicated examples, and they'll build on each other. You'll see kind of by the end how this works together. So the first example I want to give is the slender rod. So the slender rod with the moment of inertia at the end kind of looks like this. And the axis is somewhere right around the end here. All right. So here's our setup. The rod has mass M. The length of the rod is capital L. And as we usually would do, we define a density. Here, the density, there's no 3 dimensions. There's only 1 dimension. So the natural density to define is a mass per unit length, which is called linear mass density. For those of you who will continue on in 2326, this is pretty common thing that we would do in 2326. We define a linear charge density. So we'll go ahead and see this again later. But anyways, for now, lambda is simply defined as the mass divided by the length. It's some constant that defines my material. And in this case, it's just little m divided by capital L. All right, so I have my linear mass density. And if I want to solve this, what I'm going to do is I'm going to break my rod up into a bunch of little pieces. So each of these pieces is going to have a mass dm. And I will use dm, really it's just the differential of m, to denote the small mass. And it's going to have a size dx. So the size is dx, the mass is dm, and the distance from the axis is just x, the x coordinate. So if x equals 0 here, then x equals whatever is the position of one of the particles. So quickly, if lambda is mass divided by length, that'll also work here. So the mass of this object is dm, the length of this object is dx, and what that means is dm is lambda times dx. So that's how I'm going to define my differential of mass. And now I'm almost done. So I need to simply plug into this formula. I is, now it's not the sum, it's the integral. It's the integral of r squared dm. That's what I kind of flashed up during class. This is just, if I take the sum and I make it into an integral, this is the integral it becomes. And let's figure out these term by term. So first off, what is the radius between the axis and the object we're interested in? Well, that's just x. So r is just x, that becomes r squared. And dm, as I mentioned, is lambda dx. So I'm integrating over x. What are the limits of the integral? So what's the smallest value of x I can get? 0. The rod doesn't continue past x equals 0. And similarly, what is the largest value of x I can get? It's just L, the length of the rod. So I'm integrating from 0 to L of x squared dx times lambda. The lambda factorizes. The integral of x squared is 1/3 x cubed. And when I plug in the limits of integration, this becomes 1/3 L cubed. So we are almost done at this point. I have to plug in the fact that lambda is m divided by L. And I get that formula that I mentioned in class, 1/3 mL squared. Moment of inertia of a thin rod. Okay, so this gives you a sense of how these types of arguments work. I break the system up into a bunch of small pieces. Here, because it was a linear object, I broke it up into small linear pieces. I determine the relevant density in terms of the things that I'm given. So here it was the mass per unit length, later it will be the mass per unit volume. And then I simply plug in to the formula and do a little bit of regular old calculus. So we can start to make that a little bit more complicated by working on slightly more annoying type of geometry. So example number 2, probably going to be the hardest one just in terms of the actual calculus, is a thick-walled cylinder. Again, just about its center. So by thick-walled, what I mean is the following. I have a cylinder of height h. And the material lives between some inner radius R1 and some outer radius R2. So all the material lives in between these two. And then there's a little hollow core right here. And the density is going to be just some given value, which I'm not going to tell you, rho. Total mass m. All right, so let's see if we can derive this formula. Before we go and do any calculus, the first thing we need to do is figure out what's the relationship between density and mass. So in order to do that, we just need to figure out the volume of this object. The volume is actually pretty straightforward. It's just the volume of the outer cylinder minus the volume of the inner cylinder. Give me just 1 second. I'm going to go and kill a couple of these applications so it doesn't freeze quite as much. All right, so volume of outer minus volume of inner, right? Everything that's left is actual material. I subtract out that little core in the middle. And now we just need to remind ourselves what's the volume of a cylinder. So we talked about this in class. It's pi r squared h. So that's pi r2 squared times h minus pi r1 squared times h. That's my volume. Mass is m. And that means that my density rho is equal to m divided by v, or in other words, m divided by pi times h times r2 squared minus r1 squared. Density of the cylinder. All right, so now if I want to go ahead and do calculus, I need to break this up into little slices. And here it doesn't make sense to break it up into little linear chunks. I want to do something that makes sense in terms of the symmetry of the problem. So I'm going to look down on my cylinder. So here's the same thing drawn in profile view. There's R2, there's R1. And the way I'm going to break this up is into little slices at radius r, lowercase r, and of width dr. So it will be the entire cylinder. We'll break it up into little slivers of width dr, and the distance away from the center will be just little r. Okie dokie. So let's talk about that little slice. That little slice is just a cylinder, and the mass of it is actually something we can figure out. So we know the mass of a cylinder with some inner radius and some outer radius Yes, that's this formula right here. Rho times pi times h times r2 squared minus r1 squared. Well, what's the outer radius of this little slice right here? The outer radius is just r plus half of that width, dr over 2. What's the inner radius? So that's this outer radius of this little sliver. What's the inner radius? Well, it's just r minus dr over 2 squared. Now let's just do a couple of lines of algebra. This turns out to be exact, though there's no guarantee of that, but it's nice, so why not? So this is pi rho h times r squared plus r dr plus dr squared over 4 minus r squared plus r dr minus dr squared over 4. The r squareds cancel. The dr squareds over 4 cancel. I have 2 r dr. And so the small little bit of mass in this little sliver, this little cylindrical sliver, is pi rho h r dr. 2 pi rho h r dr. There are 2 of those. There's another way of doing this, which is just the width is dr, the size around the outside is the circumference of the circle, which is 2 pi r, and then it's rho times that volume, which is h times radius times circumference times width. Either way, you get the same answer, 2 pi r dr, rho h. And now again, we plug into the formula. So the moment of inertia is the integral of r squared dm, which is the integral of r squared. Well, r is the radius, is actually just the distance from the center of mass. So r is r. dm we just saw was 2 pi rho h r dr. And everything except for the r's is a constant, and it comes out front. So that's 2 pi rho h times the integral of r cubed dr. And what are the limits of the integral? So what's the minimum radius that material exists at? r1. What's the maximum radius that the material exists at? r2. So again, this is a pretty straightforward integral to do. This is now just algebra and calculus that you know how to do. So let's go ahead and plug this in. So I have 2 pi h. Let's go ahead and plug in rho. We know that rho is m over pi h times r squared minus r squared. I'm lazy. What can I say? There you go. And this integral right here, that's a quarter r squared. So that's 1/4 of r2 to the 4th minus r1 to the 4th. All right, so this is pretty straightforward now. The pi h's cancel. The quarter is going to come out front and cancel, make a 2 on the bottom. What I have when I factor everything out is 1/2 m times r2 to the 4th minus r1 to the 4th over r2 squared minus r1 squared. And now one just other quick piece of math. If I have a to the 4th minus b to the 4th, I can always write that as a squared squared. A squared squared minus b squared squared. So you may remember that that's just a squared minus b squared, so r2 squared minus r1 squared times r2 squared plus r1 squared. If you don't believe me, just go ahead and multiply this out. Check me on it. I am pretty sure on this one. And so one little piece of math here, the r2 squared minus r1 squared cancels out. And I get the formula from the book, 1/2 m times r1 squared plus r2 squared. Which in various limits, if r1 goes to 0, I get 1/2 mr squared. If r1 goes to r2, the thin-walled cylinder limit, I just get mr squared. Those are the two limits we talked about at the end of class. And in between, you just get this nice formula. All right. So that brings us to the last example, which is actually not all that hard once you've done this one, which is the solid sphere. So this is kind of the most complex bit of calculus that we would do in this level of physics, even if you were in, let's say, the honors physics track. Eventually you might go a little crazier with non-spherically symmetric things, but you know, generally speaking, this is about as far as we like to go. The solid sphere. So with the solid sphere, I have some, well, sphere of radius r. Solid means it's entirely filled with a constant density material. Radius is capital R. Mass is little m. And it has some density, some volume. Actually, let's go ahead and write that out. Is 4/3 pi r cubed. That one I am not going to derive, though you can actually do it with the same bit of physics that we're about to do, but I'm not going to bother. That's a formula hopefully you already knew. All right, so we know all of this. First off, that means that the density is mass divided by volume, so that's just 3m over 4 pi r cubed. And now I want to break this guy up into something so that I can go ahead and do my integrals. So the way I'm going to do this is I'm going to imagine that I stare down on the sphere in some particular direction. So imagine the following situation. I'll go ahead and just draw this on the drawing I already have here. Imagine my axis of rotation, let's call it the z-axis. It's just going through the center of the sphere like this, and it's going into and out of the page. So the axis is, let's say, out of the page. Okay, so you can kind of imagine this like an apple. Like an apple, this is the core of the apple is going down through one of them. And what I can do is I can slice perpendicular to the core. So if I do that, if I take my sphere and I slice it in little slices, let me see if I can draw this. This is probably going to be a pretty bad drawing, but here's my sphere. What I'm going to try to do is I'm going to try to break it up into little slices, like so. So now here is my z-axis, my axis of rotation. I'm going to break it up in little slices that are perpendicular to the z-axis. And if I look down on one of these slices, so now here's my xy plane, it's just a sphere, it's just a disk, right? It's just a thin disk of radius, let's call it curly r, for reasons, no, let's just call it lowercase r. No, let's call it curly r. And the width, the height of this is just the size of these little shells, which I'm going to call dz. So the height is dz, the radius is r, and I actually know the moment of inertia of such a disk. The moment of inertia of such a disk is actually what I just calculated. It's 1/2 the mass of that disk times the radius of that disk squared. And if we figure out what is the mass of this disk, well, the mass of the disk, I'm going to go ahead and draw this out on the next page here. So 1/2 the mass of that little disk times the radius of that little disk squared. The mass is just density times volume. So density times volume. The volume is the area of this cylinder, 4 pi lowercase r squared, times the height, which is dz. So that's 1/2 m times lowercase r squared. Or in other words, the little bit of I, I'm going to call this di because it's the moment of inertia of that little sliver, is just 2 pi rho times curly r to the fourth dz. And now I'm almost ready to go. So if this is my little moment of inertia for this teeny little slice, if I want to get the total moment of inertia, well, if I integrate a differential, I just get the total moment of inertia. This is equivalent to what I was doing earlier. So in this case, that's 2 pi rho times the integral of curly r to the fourth dz. And here z, my z-coordinate, goes from negative r to capital R, assuming z equals 0 is right in the middle, right? Because that's the radius of my cylinder. So we're almost ready to go. The only thing left to do here is to figure out what is r of these slices as a function of z. And in order to do that, all I need to know is what's the equation for a circle. So the equation for a circle, here this is this distance, lowercase r. You'll notice that lowercase r and z actually form the equation of a circle of radius r. So what I have is that lowercase r squared plus z squared is equal to the radius squared. And that means I can solve that r squared is big R squared minus z squared. So now we are good to go. We can go ahead and plug this in. Moment of inertia is 2 pi rho times the integral from negative r to capital R of r squared squared. So that's capital R squared minus z squared squared dz. And this is something you can do. It's in the notes. I don't find the algebra particularly exciting. You just basically do this integral. Yeah, what the hell? I got a couple minutes here. So that's 2 pi. The density rho we can go ahead and just copy over. That's 3m over 4 pi r cubed. Times this integral. So first off, let's go ahead and write out what this integral actually is. So this is the integral of capital R to the fourth minus 2 r capital R squared z squared plus z to the fourth dz. That's 3m over 2r cubed times the integral from negative r to capital R of, actually I don't need to write that out. Let's just go ahead and do that. The integral of capital R to the fourth dz is just r to the fourth times z. Z is 2 times capital R because it's r minus negative r. So that's 2r times r to the fourth. This next term, minus 2r squared times the integral of z squared is 1/3 z cubed. When I take that between the limits, I get 1/3 of 2r cubed. Finally, this last term, the z to the fourth term, that is r to the fifth over 5. And when I add the two limits together, I get 2 r to the fifth divided by 5. So there's a 2 on each term. I'll factorize that and cancel out the 2 up front. There's an r to the fifth on each term and an r to the cubed outside, so I'll cancel that out, and everything in here will become r squared. So if I do all of this together and haven't made any mistakes, with 1 in 10 chance, but what the heck, I have 3mr squared times 1 minus 1/3. Oops, I calculated too many 2's, so that's 2/3, plus 1/5. 1/5, sorry about that. Jumped the gun on that. Indeed, as I just prefaced, the common denominator here is 15. So that's 3mr squared times 15 minus 10 plus 1 over 15. Or if I go ahead and cancel out that 3, the denominator becomes 5. Or 1/5 mr squared times 15 minus 10 plus 1 is 6. 6/5 mr squared is incorrect. Where did I go wrong? Plus 3/15. 15 minus 10 plus 3 on the other end, 8. Dropped a factor of 4 somewhere. This is why I'm much more careful in the notes than I am in lecture. Let's see. I had a 2 there. Cancel the 2. And then there's a mysterious floating factor of 1/4 that magically floats in, cancels this out, and gets 2/5 mr squared. If you want to see it done correctly, you can take a look in the notes. I did, in fact, do it correctly there. It's the same piece of physics, but I'm probably missing a sign somewhere, and I am too tired to go back and do it right now. Alrighty, so hopefully for those of you who stayed to the bitter end, this is just a little bit extra to give you a sense of where this can go. For those of you who haven't, good night. Thanks for not hearing my mistake towards the end of the lecture. Anyways, thank you for staying, those of you who did, and I will see you guys next Tuesday. Thanks.